Good day. Today we're doing the Whoop Tune using our Micro FPV Tuning Guide, which you can download through a link in the video description below. This is the fourth video in our Micro FPV Tuning Guide series, and if you missed any of the previous three, the playlist is down in the video description as well. Last time we completed our 3-inch drone tune with our Rattler build. Then I asked you through a poll on my channel's community tab what type quad you wanted to see tuned next. The Whoop Tune was at the top of your list. If you're unfamiliar with the community tab, that's just one way I stay in touch with you to get your inputs and opinions on future content and to pass on special information as it pops up. To see community tab posts, make sure to subscribe and hit that notification bell below, and you can also just go to my channel's homepage and click on the community tab itself anytime to see the latest post. I'm going to use the same Micro FPV Drone Tuning Guide process we used for our 3-inch build. This time for our Whoop though, I've got a little something extra for you, which could increase your Whoop flight time by 30%. Sound good? Then subscribe to your TMac FPV channel, your home for your journey to better FPV fun, flights, and racing stuff. The Whoop I'll be tuning is my original Happy model, Mobula 7, which is one of the bind and fly quads I recommend on the Best Value FPV Drone Gear page of my TMac FPV site. This is the version 1 Mobula 7 though, which means it has an F3 flight controller in it. So in order for me to come up with a good tuning template for you on this quad, I'm going to need to swap out its flight controller with an F4 that has Blackbox capability. I was able to find 2 flight controllers with Blackbox capability that might fit in a Whoop. One is the Beta FPV Toothpick F4 V3 all-in-one, which has a 20 amp 4-in-1 ESC and 3 UARTs. Its physical mounting dimensions seemed slightly too big without modification for the Mobula 7 frame though, so I went with a different one. The one I chose is the iFlight Success F4 2-4S all-in-one Whoop board with a 12 amp 4-in-1 ESC, 8 megabytes Blackbox flash memory, a separate 200 milliwatt VTX, which has pin connectors, and the flight controller has 2 additional UARTs. Both of these boards, the iFlight Success F4 all-in-one and the Beta FPV all-in-one, seem like great options for your Whoop and Toothpick builds, and I've got links below to both of them. Since I'm taking time to swap out the flight controller, I thought I'd swap out the frame too. So I'll be going from the V1 frame to the V3 frame, which is a little bit sturdier. It also has this place for an LED strip, which goes right on the back like this. That's sort of cool. I've never done that before. I'm going to give that a try. Lastly, the stock Mobula 7 comes with a built-in receiver. With this flight controller I'm using, I need to use an external receiver. So for something a little bit different, I'm going to take the opportunity to make this a crossfire Whoop. Here's a chart comparing the features of the stock Mobula 7 V2, which is the one available on the market today, with the custom Mobula 7 I'll be tuning today. Both do use the MPU 6000 gyro and the BL Heli S firmware ESCs, and they both use the same 0802 16,000 kV motors. The main feature I was looking for with the replacement flight controller was this Blackbox capability to be able to do the tune template for you today. With that, let me go ahead and swap out the components so we can start our tuning process. Alright, now that we have our components swapped out and our Mobula 7 rebuilt, I flashed it with Betaflight 4.2 and enabled bidirectional D-Shot with the JESC firmware to be able to use RPM filters. If you need a refresher on how to flash Betaflight firmware or use JESC, there are links below and you can check out this video on Betaflight RPM filters. Before I go any further though, I want to make sure you get that extra 30% Whoop flight time. So the only difference between the process I described in the RPM filter video I just mentioned is for Whoops, you should flash the 48 kHz version of JESC firmware rather than the 24 kHz used for larger micros. It's a very simple process, which I'll show you now. Flash all, GH30, we have to select the version of JESC we want. Since we're flashing this to a Whoop, we want to use 48 kHz PWM, which is recommended for Whoops as you see here. 24 kHz is recommended for 3 inches and up, which we did on a previous build. So for our Whoop, we're going to select 48 kHz, and that should give us an increase in flight time of about 30%. Next, we go to our Micro FPV Tuning Guide, and since our Mobula is a Whoop, we look at this side of the chart and notice that we want our PD and feed forward gains to be higher than what the default values are, and our I gains to be lower. But before we get to the PID settings, the first thing we want to do, according to our tuning guide flowchart, is to enable the RPM filters and adjust the dynamic notch filter settings. So let's go ahead and do that first. We go to our filter settings tab. We enable the gyro RPM filters, keep it at 3 and 100. We want our dynamic notch width percent to be 0, which gives us 1 notch filter. We want our Q to be somewhere between 200 and 250. I'm going to set this at 200. And once again, according to our guide, we want our dynamic notch min 100 and our dynamic notch max to be 200. We're going to leave both our gyro and D-term low pass filters on the default value, and we click save. Okay, we want to go to our PID profile settings and back to our tuning guide. It says for low authority whoop quads, make sure D-min's toggled off under the PID controller settings. So we toggle D-min off, which will combine D-min and D-max into only one D value, as you see here. We'll save that before we forget. And then we want to move the master multiplier slider to 1.5 and the stick response gain to 1.6, hitting save after each. Master multiplier slider to 1.5, hit save. Stick response to 1.6, hit save. PD balance to the right 1.5, hit save. And then we'll type in 34, 34, and 90 is the default. So we're going to go 34, 34, 90. Hit save. And then from here, according to our flowchart within the Micro FPV tuning guide, after we've adjusted our filters and our PIDs, we want to take it out for a test flight. Check the motor temps, do a couple flips and rolls, and see how she flies with our baseline tune. So let's do that and come back inside and take a look at it. Okay, I've done a short test flight and checked out our motor temps and they're fine. Then I did a couple 180-degree turns to check for prop wash vibrations, a flip or two, and a couple rolls. I've then uploaded our flight data file, or Blackbox log, from our flight controller's Blackbox, and to save time for this video, instead of showing you separately the full flight, I've decided just to sync up the flight video from my goggles DVR with a flight log like we did last time. The graph setting I'll be using to check out both how our filters are doing and also our PID settings are the same we used last time and for the same reason. So if you're unclear as to how to set these things up or why I'm doing it this way, please check out the other videos in this Micro FPV Tuning Guide playlist through the link in the video description below. Alright, first, let's see how our filter settings worked to get rid of noise in our gyro signal. First, the roll axis. Let's look at our unfiltered gyro signal, then our filtered gyro signal. So what we're looking at here is our unfiltered gyro signal with a max motor noise of 331 Hertz. We click over here, and this gets our filtered gyro signal, and you'll notice most of the noise goes away. We still have max motor noise at 330 Hertz, which is a little bit interesting to me. But it did a fairly good job. How about our pitch axis? Unfiltered and filtered. Boom. Wipe that out. That looks good. That's what I like to see. I wish the roll axis looked more like this. What about yaw? Unfiltered? Look at all this stuff over here. And filtered. Boom, gone. That's those RPM filters for you. Nice. So based on this quick analysis, 2 of the 3 axes looked pretty good. I'm not really happy with the roll axis though, and I think we can do better. In part 2 of this series, Blackbox Explorer Basics, I mentioned a couple ways we could deal with leftover noise in our gyro signal. Remember, our peak motor noise on the roll axis is 330 Hertz. Let's take a look at our filter settings. So these are our filter settings that we've used for our baseline tune and our first test flight. Well, it looks like the simplest thing for us to try to take care of, that max motor noise at 330 Hertz, is to bump our dynamic notch max Hertz up from 200 to at least 330. So let's go ahead and put this at 350, just to be conservative. Hit save, and that's all I'm going to change, and it should take care of that max motor noise on the roll axis at 330 Hertz. After our second test flight, we'll see if that takes care of it. Now let's look at how our PID settings are doing for our whoops performance. Alright, now here I've set up our graph to show our stick commands or our set points on the roll, pitch, and yaw axes, as well as our actual quadcopter's movement on the roll, pitch, and yaw axes, which is described by its gyro on each of those axes. If you recall from previous videos in this series, our quadcopter's actual movement is going to be slightly different than what we command it to do. Obviously, we would like the difference to be as small as possible, and we want our quadcopter's actual movement to track as closely as possible to what we command it to do. We minimize that error between its actual movement and its commanded movement by adjusting our PIDs. So let's take a look at our quadcopter's actual movement in comparison to its commanded movement, or our stick commands, on each of these axes for those 180-degree turns, a flip, and the rolls. And when we're looking at our graphs to make a decision as to how we want to change our PIDs, if at all, we go back to our tuning guide flowchart in our Micro FPV tuning guide, and this is the step we're at. We're observing through the black box analysis, and we're going to adjust our PIDs looking for any of these things. We're going to be looking on each of those axes, roll, pitch, and yaw, for high frequency oscillations or shudders, bounce back if you will. And if we get that, we can either decrease our P term gain or increase our D term gain. We're also going to look for prop wash alone by itself, or also with overshoot. If we have that, we can increase our D to take care of that. If we're noticing that we have the same consistent error on any of the three axes between our set point or our stick commands and our gyro, or our actual quadcopter's motion, then we should probably consider increasing our I term gain. And if we want our quad to be more responsive and or reduce the time delay between when our quadcopter is commanded and when it actually makes the commanded movement, then we should probably increase feed forward. So first, let's take a look at the 180-degree turns, and we're going to look for prop wash, and if we see any, then we should probably be thinking about increasing our D term. Then we'll take a look at the flip and a roll and see if we get any shudders or bounce back, where we should consider decreasing P or increasing D. And if we've got excessive time delay, then we'll also look at increasing our feed forward. So first, the 180-degree turns. Coming up on one here. And right there. So let's take a look at our roll axis. Back here you can actually see a little bit of oscillation, and that's the vibrations due to prop wash. So we do see a little bit of prop wash vibrations, which we might want to consider increasing our D term for at least the roll axis. Let's take a look at the same position for our pitch axis. That's pretty darn good. I'm not going to complain about that. And what about yaw? That's dead on. So out of those three axes, it looks like we could consider increasing D for our roll axis. Let's go ahead and take a look at the next 180-degree turn. Right there, and it looks like we're seeing the same thing on our roll axis. Yep. And what about pitch? A little bit, not too bad. So right now I'm thinking about increasing D on the roll axis and maybe a little bit on the pitch axis. Yaw, I'm not going to touch. Let's go to our flip. Coming up on it, and there it is. Right here on our roll axis, you see a little bit of that oscillation, so we go back to our chart, and we do see some oscillations or shudders, so we might consider increasing D because of that, and if we increase D over here due to the prop wash, it might also take care of that as well. Let's see if we should be decreasing P, and the reason we should be is if we've got excessive overshoot, which it does not appear that we do. This is actually not much overshoot. It's actually just shifted to the right on the pitch axis. This is delay. There's not much overshoot here, a little bit, but if we increase D, it should be able to get rid of that a little bit of overshoot as well. But we might want to increase feed forward some more. All right, let's take a look at a roll. Got a little bit of delay, a little bit of overshoot. If we increase D to take care of that prop wash vibrations, it should inhibit some of this overshoot. And if we increase feed forward, that should get our response time better for our actual quadcopter movement to more closely track our commanded stick position movement, which would narrow this gap. It should actually make the slope of this line come down steeper and more closely track our stick position with increased feed forward. So once again, I'm looking at increasing D at least on the roll axis, slightly on the pitch axis, and increasing feed forward. All right, here's what we're going to do then. We're going to make a few changes in Betaflight. Go to our PID tuning tab. Now, when we changed our numbers manually for our I-term gains, that disabled the sliders. If we enable the sliders now, it's going to wipe these out, unfortunately. So I'm not going to enable the sliders to do this. I am going to increase D on the roll axis and slightly on the pitch. So here's what I'm going to do. I'm going to increase D on the roll axis by 10 and on the pitch axis by 5. Then I'm going to increase feed forward by 10 on the roll and the pitch axis. So on yaw, feed forward, I'm going to increase this by 5. I'm going to go to 221. All right, so we increased our D term on roll by 10, pitch by 5, and we've increased our feed forward terms on all 3 axes. We're going to click Save, take it out for another test flight, and see how these PID settings work for our refined tune to improve the performance of our Mobula 7, and also see if by changing this value to 350 on our dynamic notch filter, if that takes care of that max motor noise at 330 Hertz. So let's take her out for another test flight, come back, and we'll check those things out. All right, to save some time, here's what I've done. I took her out for our second test flight with the increased D and feed forward values, which I just talked about, and you see over here on the left, along with our new dynamic notch filter max hertz of 350 to take care of that motor noise at 330. Although there were some improvements in all areas, it wasn't quite enough for my satisfaction to give it to you as a template. So I made the following changes over here on the right for a third test flight. On the roll axis, I increased our D term by just another 5 points to get rid of just a little bit more of the oscillations, and I added 12 more points of feed forward to try and get rid of a little bit more delay, and just to make it the same as on the pitch axis. I kept the filter settings the same. Remember, our gyro and D-term low-pass filter settings are still at the default values, which we could move to the right if we chose to try and reduce any further delay. For now, let's see how our PID and filter settings did on our third test flight as compared to our baseline tune. All right, the first thing we're going to check is how our increased max hertz on our dynamic notch filter of 350 did as compared with its setting at 200 to get rid of that motor noise at 330 Hertz. So over here on the left, we have our baseline tune. Let's go ahead and take a look at the gyro signal noise. And here we have our max motor noise at 330 Hertz with the max frequency setting of our dynamic notch filter at 200 Hertz. On the right, you see that with our max frequency setting of our dynamic notch filter at 350 Hertz, it got rid of this stuff at 330, and now our max motor noise is at 158. I'm going to call this a win, and I'm happy with those settings. Now let's take a look at our 180-degree turn, a flip, and a roll quickly to see how our new PID settings did. All right, over here on the left we have our baseline tune, and over here on the right is our new tune, and these are set at approximately the same point in our 180-degree turn. So let's go ahead and take a look at the roll axis for our baseline tune, and you see here's our oscillations that we were trying to get rid of. With our new tune, you see those oscillations have been diminished by that increase in our D term. We'll take a look at the pitch axis. It's not bad over here. And over here it's tracking nicely. And our yaw axis. Sweet. So for our 180-degree turn, we've made significant improvements in getting rid of our prop wash vibrations from our baseline tune to our refined tune. Okay, for our flip, we're at approximately the same position for both our baseline tune and our refined tune. And let's go ahead and take a look at the roll axis. And over here on our refined tune, it seems to be tracking a little bit better than over here on our baseline tune. A refined tune seems to track our commanded stick movements a little bit more closely. Maybe not too much difference on our roll axis. Let's take a look at our pitch axis. It honestly looks about the same from here to me, but if you notice coming out of the pitch, we've got this much difference between our commanded stick position and our actual quadcopter's movement. By increasing our feed forward, I believe, what we've done is we've actually narrowed that gap. So as you can see, we're coming out of the flip here, and our actual quadcopter position is more closely tracking our commanded stick inputs as we're exiting the flip. So we've made progress on the flip maneuver with our refine tune as well, especially on the pitch axis. And once again, on the yaw axis, we're tracking fairly well. All right, now let's take a look at our roll. We're at approximately the same position for both our baseline tune and our refined tune. And we can already see just from this view that this gap over here has been narrowed on our roll axis. These major blips over here have been minimized, and it looks like we're tracking much better on the yaw axis. So if we zoom in on our roll axis, we're tracking nicely. On our pitch axis, as I mentioned, these big oscillations over here are basically gone. And on our yaw axis, comparing our baseline tune with our refined tune, I would say our new tune is tracking quite nicely. We did good. So that's our completed Micro FPV tune for our Mobula 7 Whoop. As with all the Micro FPV quads in this series, the PID and filter setting CLI commands for your Whoop tune template are available through a link below. Remember to grab your Micro FPV tuning guide down there too. For more good stuff to speed you on your journey to better FPV fun, make sure to check these out next. Thanks for your time. I'll see you next video. Clear skies, friend.